Good day, my little chemistry wizard, and welcome back for your last lesson of the year. Yes, it is the last lesson. Woohoo! Okay, so let's start. Solubility product constant. It's another type of constant, obviously, about equilibrium. What kind of equilibrium? It's when we dissolve a solid in water. We know that an equilibrium is attained when we start seeing a little bit of solid at the bottom of the container. So when we attain the saturation point, that's when the equilibrium sets in. So if we look at an equation, an actual dissolution, we may have, for example, BaSO4 solid that we put in water. It will dissociate to form Ba2 plus and SO4 2 minus. So if we want to calculate the KSP, or the solubility constant, we will do products over reactants. But we very well know that the reactant is a solid, so we do not include it in the calculation of the KSP. So we end up with just the cation and the anion, both concentrations being multiplied together to get the KSP. So the general format would be the following. We have a salt that dissociates into a cation and an anion, and that's basically what we use for the calculation of the KSP, each ion being to the power of its own coefficient. As usual, if the KSP is small, that means that there's not much dissolution, there's not much reaction. So the solubility is low, and that's a sign of a weak electrolyte. If the KSP is large, if the value is large, the solubility is high. So I have a very strong electrolyte. It will dissociate a lot, will conduct electricity very easily. Now you have some sample problems in the textbook. I will not go over them. I'll show you other examples, but you may take a look at them. I actually encourage you to do so. Now, first example of 3. It says, calculate the KSP of thallium chloride at boiling water temperature, where the concentration of a saturated solution is 2.4 gram per 100 milliliter. So the first thing you need to do is to figure out what the dissolution reaction is. So I have TlCl solid. I put it in water. What do I get? I get Tl plus 1, Cl minus 1. So the calculation of my KSP would be Tl to the 1 times Cl to the 1. Now, since I'm given a concentration in grams per 100 milliliter, I need to convert that into moles per liter, which I did over here, 100 ml to get the mass per liter. And then I took that mass over the molar mass to get the number of moles. I plug those numbers into the KSP. Since the ratio is 1:1, I get 0.01, and as usual, there's no unit for the KSP. That's a simple example. Let's move on to a slightly more difficult one. So the next one is the following. Calculate the KSP of calcium fluoride at 20 degrees Celsius, where the concentration of a saturated solution is determined by evaporating a 100 ml sample of saturated solution of 2 dryness. A mass of 0.0016 grams of solid remains after evaporation. So in this case, it was already at equilibrium, but to find out how much we had dissolved, we evaporated all the water to find out how much solid we had originally dissolved to obtain that equilibrium. So again, the first thing we need to do is to write down the equilibrium reaction. So we have CaF2 solid that dissociates into Ca plus 2 and 2F minus. Next thing we do, we convert our mass of CaF2 into a molar concentration. So in this case, we had 0.0016 grams that were dissolved into 100 ml of solution. So if we convert this into a molar concentration, I'll spare you the calculations, you know how to do this. We get 2.05 times 10 to the negative 4 mole per liter. Now, since the ratio is 1:2, at equilibrium, I would have the same molar concentration over here, but I'd have double over here, which means that when I do my calculation for the KSP, not only will the two numbers here and here be different, but don't forget, it's to the power of 2 for fluorine, so I have to square this quantity. So 2.05 times 10 to the negative 4 times 4.1 times 10 to the negative 4 squared will give me the value of my KSP. Here you go. Last example. Mercury 1 chloride dissolves as shown by the equation So this is the equation. Calculate the mass of compound required to make 500 ml of a saturated solution of mercury chloride at 25 degrees Celsius. And I'm giving you the KSP, which is 1.5 times 10 to the negative 8. So for this one, you're going to have to work slightly backwards. Again, the first thing we want to do normally is to write down the equilibrium reaction, which we already have, so we can skip that step. Next, we're going to write down the KSP law. So the KSP is the concentration of Hg2 plus 2 times the concentration of Cl minus squared. Why? Because it forms two anions when it dissociates. Now, I'm given the value of the KSP, 1.5 times 10 to the negative 8, so I replaced here. Now, my problem is I don't know my concentrations at equilibrium. So what I did is I said, okay, let's pretend I created X. That implies that here I would have created 2X, and which means X was put into the container originally, which dissociated after the fact. So if I replace with X and 2X and I square that because of the coefficient of 2 over here, I get 4X cubed. I can solve for X, which gives me 1.55 times 10 to the negative 3 mole per liter. Now that I know this, I have the original concentration of my Hg2Cl2. Now, if we refer back to the question, it says calculate the mass of compound required to make 500 ml of the solution. So I have my molar concentration, but they only want 500 ml. So let me do a little bit of conversion. So first of all, I'm going to find how many moles I have when I have this concentration. So I found that I have 7.77 times 10 to the negative 4 mole if I have 0.5 liters rather than 1 liter. So again, they're asking for half a liter. They're asking for 500 ml. So if this is the amount of mole for 1 liter, I have this amount of moles for half a liter. Now they're asking me for the mass, not the number of moles. So I'm going to take this number of moles and I will convert it into a mass using the molar mass. And I get 0.37 grams of Hg2Cl2. That's the mass that was dissolved in order to form 500 ml of the solution at the concentration that we found over here. So again, the answer, 0.37 grams. And that's it for us. That's the end of your very last lesson of the year. I wish you good luck with your final exams. It was a pleasure teaching you, and my door is always open, so don't be shy to come by and say hello from time to time. Bye.